So now let's work with solving linear equations. Okay, so so far we've met with algebraic expressions. Okay, now we're going to look at equations, and because they're equations, they have an equal sign in the term. So generally, it means that when we have the word solve, it generally means that we're looking for a numerical value of x, not simplify but solve. Okay. So here's an example here. Solve 3x minus 1 equals 8. Okay, so we need to isolate the x term. So to do that, we first of all bring the minus 1 over, it becomes plus 1. So we have 3x equals 8 plus 1 is 9. Now we need to isolate the x from its coefficient, which is 3, and the best way to do that is just to divide both sides by 3. So they'll cancel and we get x is equal to 9 over 3. If 3x equals 9, if I divide both sides by 3, then x is equal to 9 over 3 is equal to 3. Okay? And we can check to see did we get the right value for x by just plugging it back in. 3 times 3 is 9 minus 1 is 8, so that's correct. Solve 3x plus 1 is equal to 5x minus 13. So the x term, normally I like to keep the x's on the left, but the x term in this case is larger on the right. So to keep that positive, we'll keep the x's on the right. So we have to gather the x terms and then isolate x. So the first thing to do is bring over the 3x, so it's minus 3x. Bring over the minus 13, it becomes plus 13. So 14 is equal to 2x. X is equal to, divide both sides by 2. 14 over 2, x is equal to 7. And again, if you put that back in there, you'll see that this side holds true and is equal to that side when x is equal to 7. Now, sometimes we might be given a shape like this rectangle here with x plus 4 is the length of one side and x is the length of the other. And we might be asked to, to generate a linear equation, to write out an expression for something like the perimeter of this rectangle. So the perimeter would be equal to x plus 4 plus x plus 4 plus x. Okay, so what we have in fact is we remove the brackets, x plus 4 plus x plus x plus 4 plus x. As we gather our like terms, our x's and our 4's, and we see that the perimeter p is actually given to be equal to, as a linear equation, p is equal to 4x plus 8. Now, they might say, if p is 20, find that value of x. So in that case, 20 is equal to 4x plus 8. So 4x is equal to 20 minus 8, which is 12. X must be equal to 12 over 4. X is equal to 3. Now, algebraic fractions always seem to be tricky for people, but let's just look at one way we can approach these. Okay, adding or subtracting algebraic fractions. So here's an example. Express 3x minus 1 over 3 plus x minus 5 over 2 as a single fraction. Well, the first thing I do when I do these is I draw my line and I write whatever's underneath each fraction here. So I write 3 and 2 beside each other. It's okay, just leave them in their brackets like that. Then I draw what I call 4 containers, 2, 3, 4, and I divide them or separate them by the sign here, the plus sign. Okay? Then I write this value in the top left container, and I write this value in the one immediately after the sign. And then I look to see, I say 3 goes in here, I cover the 3, goes in 2 times, and 2 goes in, cover the 2 3 times. Okay? So you cover 1 and you write what you see. Okay, so you say 3 into, cover it up, and you write 2, and then you say 2 into, and you cover that up, and you write 3. Okay, so we end up with 3x minus 1 times 2 plus x minus 5 times 3 all over 3 times 2. So just rewriting that up here again. Now let's remove the brackets. So 3x by 2 is 6x, minus 1 by 2 is minus 2, x by 3 is, actually I'm going to stay safe and do this calculation here in this bigger bracket. So x by 3 is 3x, and x by minus 5 is minus 15. Okay, all over 3 times 2. So that's equal to 6x minus 2, and then we can remove these brackets, and it's just, there's a plus sign here, so it's fine, the signs stay the same, plus 3x minus 15. Let's gather the terms, so we get 9x minus 17 over 6. That's that fraction reduced to a single fraction. So here's the next step, if you like. We rewrote previously the fraction into a single fraction, and often we're asked to solve linear equations with fractions. Okay, so when we say solve now, we're actually looking to find a value for x. So let's say we have something like x over 5 minus x minus 3 over 6 equals 3 over 2. Okay. First thing I do is I'll just stay working on the left side. I'll leave the right side as it is for a while. Okay. I'll just stay working on the left. I take my 5 and my 6 and I write them there. I do my 4 containers, my sign, okay, and I write what I see here, there, and I write what I see there, there, and then I say 5 goes into cover the 5 6 times, and I say 6 goes into cover the 6, and here is the 5 times. Okay. Then I remove the brackets by multiplying. 6x is 6x minus, and again we'll stay safe here now, we'll say 5 by x is 5x, and 5 by minus 3 is minus 15. All over 5 times 6, which is 30, still equals 3 over 2. So now I want to remove these brackets, my next step, and I'm very careful now, always the minus sign. Minus is, beware, it's where people fall over. I have a minus sign outside the brackets, and we learned in the first video that that will change the signs of the terms inside the brackets. So that's 6x minus 5x, minus by minus is plus 15, all over 30. And that's where people go wrong every time. Okay, so be careful always with the minus sign outside the brackets. So we've all of this is equal to 3 over 2. So now we can cross multiply, because we've one fraction this side and one fraction that side. We can cross multiply. So 30 times 3 is 90. 2 by 6x is 12x, minus 10x, 2 15s is plus 30. Gather up with 12x minus 10x is 2x, and that's all equal to 90 minus 30 is 60. X is equal to 30. So the containers is one way of approaching solving linear equations with fractions. But another way, and I'll just show it to you, it might suit some of you more than others, is to look at your denominators under the lines. You have a 5, a 6 and a 2. And if you multiply all the 3 terms by whatever 5 by 6 by 2 is, it's 60. Okay. Now if there was x's here as well, it would be 60x. Okay, you multiply by that as well. But let's just keep it simple now and stay with this. So if I just rewrite the fractions out as the original term and put 60 beside each one, okay, you can see that 5 goes into 60 12 times, 6 goes into 60 10 times, 2 goes into 60 30 times 3 is 90. And so minus 10 by x is minus 10x, and minus 10 by minus 3 is plus 30 is equal to 90. So 12x minus 10x plus 30 equals 90. You know, that's where we were here. It's kind of faster this way here, but it might not suit some of you. You might get confused, and you might be better off with the step-by-step method. Okay, it's up to you. But either way, 2x equals 60, x is equal to 30. So there's 2 ways to work with these. Either multiplying all the terms by the product of all the 3 denominators, or else do it the contain. I call this the containers way. Okay. Let's talk about linear inequalities. Okay. In this case, in the next while now, we're going to be using linear inequalities to solve for x. But x won't be a single value. It'll actually be a range of values which we note on a number line. Okay, so there's different symbols that we meet with when we meet with linear inequalities. There's the, and I'm going to read from left to right, but there's the greater than or equal to. X is greater than or equal to y. There's the less than or equal to. X is less than or equal to y. There's just the greater than. X is greater than y. Or the less than. X is less than y. Okay? And there's a few rules we have to consider and types of numbers we're going to be working with. So I just want to mention those first before we do some examples. But when we work with linear inequalities, we'll be working with natural numbers. They're the whole positive numbers, and that will be signified if we see that x is an element of the set of natural numbers. That's what this mathematical notation means. That's all it means. We'll meet with integers, whole positive and negative numbers, and we'll know they're integers because it will tell us that x is an element of this set of integers, z. We'll meet with real numbers, and real numbers are all numbers basically, the positive, negatives, whole numbers, decimals, fractions. They're the whole range of numbers. Every number is a real number, okay? But not every number is an integer and so on. But we'll know the real numbers because we'll see in the problem that x is an element of the real numbers. They'll have that written in the example. And when we go to graph this thing called the number line, we'll be writing or describing the range on the number line one way or the other. We'll come to it when we do it by example. The question will say, okay, in this problem, x is a natural number or x is an integer. If it says that, we're going to use dots. Bear with me, I'll explain dots in a while. If it says that x is a real number from the set of real numbers, then we're going to use a really thick line. Okay, and that line's going to start with either a full dot if there's a less than or equals to or a greater than or equals to symbol in the question, or an open dot if it's a greater than or less than symbol in the question. Okay, so these just little rules we'll just do by example and they'll all come together for you hopefully. But if you can also then, I always like to keep x to the left in the problem because at the end of the problem, whichever way the inequality sign is pointing, that's the way we're going to mark our number line. Okay, so that should become clear as well. So it points your dots or lines in the right direction if you keep x to the left of the inequality sign. We're going to work with these now in the video Algebra 3.